Luis, can you hear me?
I do.
Yeah, so, okay, now we can see you. So please go ahead and do your presentation, and please try to remember it's 20 minutes, including the questions.
Okay. Let me see if I can share my screen. Okay. I think that you can see, I guess. Yes, I see myself here. Okay. Okay, good. So thank you very much. So today, in today's talk, I'm going to speak about how to combine machine learning techniques with quantum chemical computations in order to obtain better predictions in the context of calculation of electronic spectra. So why do I want to compute on spectra? So there are many reasons. Many reasons are there are researchers, but in our particular group, we are focused in one particular project is into understanding the photochemistry of chemical compounds of interest in the atmospheric chemistry. Some of these compounds cannot be measured experimentally because they are too short-lived, and then you need to do calculation in order to compute their properties. For example, if you want to compute the photolysis rate, you need, among other things, the absorption spectrum. And so that's the reason why you need to compute with precision this kind of spectra. So there are different techniques to do this. And this one that has been attracted a lot of attention along the last decade, which is the Nuclear Ensemble Approach. In this case, what you have to do is to sample a number of geometries around the optimized structure using a Wigner distribution or other techniques that we will hear about in this meeting. And for each of those geometries, you have to compute the vertical excitation energies and the dipole moment or the oscillator strength to whatever your level of quantum chemistry model. You can use OpenMULCAT or whatever you want. And so the total spectra is calculated as the sum of the individual contributions of each of those geometries, and each of those geometries contribute with a normalized Gaussian that has a characteristic bandwidth, which is we call the empirical bandwidth. So the problem is, how do we choose this bandwidth or this delta? Because if it is too narrow, we will have vibronic noise or artificial vibronic noise, and if it is too wide, we will over smooth the emission spectra. So we have to find a compromise to obtain the best shape for the spectrum. And this is typically done manually, but that's not ideal because that's very, very subjective. It depends on who is the one who selects this delta. So along these years, there has been some attempts to try to avoid this subjectivity. And in an ideal world, what we would do would be to sample millions of geometries and to run the calculations. And then in that case, we could reduce the bandwidth to almost zero. The problem that this is impractical for high-level quantum mechanical methods because it would take endless, and still you need to estimate subjectively this delta. It will be close to zero, but not zero. To avoid this problem, there are some attempts based on supervised machine learning approaches, which they are very successful. And in this case, what you do is do the quantum chemical computation for hundreds or thousands of geometries, and you use this information to train a machine learning model or a deep learning model so that it learns the function that maps the geometry coordinate space onto the absorption properties space in such a way that once it's trained, then you can present the model with other structures, and it can predict which are the absorption properties of that geometrical structure. In such a way, you can have thousands and tens of thousands of new geometries without quantum chemical computations. The good thing is that, again, you can make almost zero the delta, but the problem is that it usually fails for small data sets. If you have less than 500 quantum chemical computations, the machine learning algorithms start to fail. And again, you have to estimate subjectively the delta. There are other family of algorithms based on unsupervised machine learning. in which they forget about the geometrical information of the molecules and just focus on the absorption properties, on these values. And then they select the delta as a function of the number of geometries that you have and the spread of the transition vertical energies, the spread, or if you like, the standard deviation or the histogram of these values. And there are a few equations to do this, but we will be using one that we call Autodelta, which basically relates the bandwidth with the number of geometries and the spread of the energies. And in this case, as you see, it depends inversely on the number of geometries. So that if you have an infinite number of geometries, then your delta goes to 0. That it is what we would expect. So the good thing of this is that you have an objective estimation of delta, and each band that you compute has its own bandwidth. And that's very good because then you have a better prediction of the whole spectrum. The problem is that still we need an empirical broadening, or we are assuming that we have an empirical broadening, and we didn't like that idea too much. So accordingly, we decided to do a different approach based on Gaussian mixture models, and we end up with an algorithm that we call GMM-NEA. The results that I'm going to explain are all summarized in this publication that has been recently accepted, and I invite you to have a look at it for more details. But today I'm going to show you a short introduction to Gaussian mixture models. Then I will show you in a slide which is the philosophy behind GMM-NEA. I will go through some examples and results, and finally I will show you about a tool that we have developed to compute NEA spectra from scratch. Okay, so strictly speaking, Gaussian mixture model is a probabilistic model that assumes that all data points in a sample are generated from a mixture of a finite number of Gaussian distributions with unknown parameters. So I know this is confusing, but let's see some examples. So in a typical machine learning task is clustering, that consists in finding groups or cluster of points sharing a common characteristic. And this group could be customers, voices, images, genes, and other things. And in the case of Gaussian mixture models, it will assume that each of these groups is represented by a Gaussian distribution. Or in this case, we could say that a Gaussian distribution is a representative of a given group. There's another task in machine learning, which is classification. This that one, given a new observation that you don't know where it belongs to, you have to try to assign it. So once you have performed a clusterization task and you know which are your groups, if you use Gaussian mixture models, you can know which are the boundaries separating these groups. Accordingly, if you have new observations like this green star or the red star, you know that if it ends up here, it belongs to the red points. So those are the most prototypical examples of use of Gaussian mixture models in machine learning. But we are most interested in the density estimation capabilities. In this sense, what Gaussian mixture models allow you to have is to know which is the probability density function underlying this distribution of points, or the other way around, know the distribution from which these points have been drawn or sampled. And mathematically, it's just basically that these points are distributed according to a sum of normal distributions, which are characterized by some means and a variance covariance matrix. And so the goal of this algorithm is to try to fit these parameters from this experimental point, if you like. Okay, so then let's move to the philosophy behind GMM. Our initial hypothesis is that once you have your quantum chemical computations and you have your values from the vertical excitation energies and dipole moments, if you could know which is the probability density function underlying this point, then you can use the statistical properties of the PDF to sample new values of excitation energies and oscillator strength in such a way that you can somehow simulate thousands of new geometries and values of transition energies and oscillator strength. And accordingly, you could assume that your empirical broadening goes to 0. And as I have just shown you, this step is basically to fit a Gaussian mixture model. So our original task was to, okay, let's find which are those parameters so that we can know the PDF, and then we can sample a lot of new points and to have a more precise spectrum. But it turns out that you can modify mathematically this expression so that it depends on this probability density function. And then you can transform it even further mathematically, and you end up arriving to a new expression for the absorption spectrum that depends only on the parameters of the Gaussian mixture models. And indeed, if you see, the original expression depends on the empirical broadening, but our new expression does not depend on the empirical broadening. So we don't need, we not only don't need to define a broadening, but we don't need it anymore in our assumptions. And so actually these equations are the most important or the most relevant result of our contribution. And it is what we call GMM-NEA. Okay, so let's go to some examples. In this case, we use data that were already computed in the literature. It corresponds to benzene using TDDFT, and they assume 10 transitions. And while they computed 50,000 cases or geometries, we only use 250 geometries to reconstruct the spectra to see how it worked with small geometries. And we wanted to compare our algorithm with Autodelta, which is the algorithm that I have showed you that computes automatically the empirical broadening. And as you see, both of them perform well, but GMM-NEA renders a smoother spectra, and it seems that they are slightly more precise. But in order to see if they are more precise, this is better to go transition to or band to band or transition to transition. And if you see, and you focus in transition number 3 and transition number 9, you see that GMM is, which is the red trace, is much more precise than the green trace, which is Autodelta. And here you can see visually that GMM work better than Autodelta, but we can quantify that. So there are metrics to assess this. We use one which is called the relative integral change, which is basically it measures how similar two spectra are. And it's just an integral, but it basically is which is the area between the two spectra that you are comparing. In this case, we will be comparing the reconstructed spectra using Autodelta, GMM-NEA, and the correct model, which is existing supervised machine learning algorithm used to reconstruct this kind of spectra. And our reference spectrum will be that generated with 50,000 geometries. And I have to say, if both spectra are equal, the RIC will be equal to 0. So the closer to 0, the better. In this case, what you can see is that when you use a lot of geometries for the reconstruction, the spectral reconstruction is better and better, and this is obvious. But the most important fact in this graph is that GMM reconstructions are statistically better than those of Autodelta and especially the correct model. In fact, the correct model is a much worse performer overall at the small data sets, so a small number of reconstruction geometries. Okay, so these previous examples were based on TDDFT, and here I show you some examples of reconstructions done with OpenMULCAT calculations that we have performed in the past. In particular, we have a mercury compound, which is of interest in atmospheric chemistry, and as well we have the uracil radical. And you can see in both cases that the reconstructions with GMM are smoother than those of Autodelta, and that's good. That means that it's a better reconstruction. And I would like to highlight that for uracil, with just 100 geometries, we are already obtaining a very accurate or very nice looking absorption spectrum overall with GMM-NEA. Okay, now let me introduce you Multispec, that stands for multi-configurational spectroscopy, which is a tool that we have developed in our group for predicting electronic spectra, and speaking about ground and excited state absorption, spontaneous and stimulated emission and transient absorption with multi-configurational quantum chemistry and the NEA technique. And it works both in gas phase and in condensed phases using explicit models for the solvent. So this software is based in these two references that I will show you later if you are interested, but that you can find as well in our GitHub repository. So the idea is that once you have downloaded the program and execute it, it will generate a structure of folders and containing template files and shell scripts that guide you through the calculation. Starting from the XYZ file, it will optimize the frequencies and the geometries using Gaussian. Then it will perform a Wigner sampling using Newton X, and it will perform the spectral or the vertical excitation energies and oscillator trends calculations using OpenMULCAT to the desired level of theory. And finally, as is currently implemented, all the results from OpenMULCAT will result in a spectra using the classical NEA, classical in the sense that you have to manually select the empirical bandwidth. But eventually, there will be a folder here with GMM-NEA so that you don't have to do it manually. So currently, what you have to do is to remove the data from the OpenMULCAT folder and to copy them into your spectral reconstruction folder and to do it independently. Okay, so to summarize, just to say that I have shown that to refine NEA spectra, it is not necessary to resort to fancy supervised machine learning algorithms like the Craig model or SHNet. And importantly, GMM-NEA avoids the annoying manual determination of the best empirical broadening delta. And in fact, what it is most important, it avoids the assumption of a phenomenological broadening. Sorry. Both GMM-NEA and Autodelta reconstruct each band independently, meaning that the total spectral reconstruction is going to be more precise. For small data sets, we are speaking hundreds, GMM-NEA statistically outperforms both Autodelta and the Craig model. And finally, I invite you to use Multispec, and I will tell you that in the future it will be interfaced with GMM-NEA. But for the time being, it is implemented independently, and we have used the programming language R, and we have made an extensive use of the library M-class, which is a library to perform GMM fittings. And you can find the details on how to install it and how to use it in both my repository and that of the group. And with that, I would like to finish. Well, I would like to thank Daniel Roca-Sanjuán, which is my supervisor, for giving me the opportunity to embark in this project. And I would like to thank the QSEXVAL group, and especially Javier Carmona for his help in some steps of the project. And that's it. Thank you very much.
Yeah, thank you very much for being on time, Luis. Questions? Do we have any questions in the chat? No.
The oscillator strength, do you use the dipole moment approximation and the full operator?
Okay. Could you repeat the question?
So,
please.
Computing the oscillator strength, you could either use the dipole moment approximation, or you could use the exponential expression of the transition operator and compute the transition moment.
Yeah. Okay, so actually, I cannot answer that question because I'm new to this kind of programming, so I didn't perform the quantum chemistry computation, and I could say that I'm the machine learning guy, and so I cannot answer that particular question. So I'm not sure, but I guess that as long as this is, I don't know if I guess it all depends on the precision that you want.
All right, thank you.
Okay, then we thank speaker again.